Turns out there is a massive underground aquifer at the crest of the Central Oregon Cascades. University of Oregon scientists found the body of.
Here in Washington, we have our own volcano threat in the Cascade Mountains. This range, nestled in the Pacific Northwest, erupts on average once or twice every century. The Cascades have long been a hotspot for geological activity. Their towering peaks and fiery volcanic history have captivated scientists and adventurers. Groundbreaking technology from the USGS has uncovered something far more sinister than magma. Using advanced LiDAR scanning, researchers have peeled back layers of this rugged landscape. What they've discovered is as chilling as it is unexpected. This isn't just another volcano warning. The findings reveal an ancient and potentially catastrophic force hidden deep in the Cascades. This force could spell disaster in ways we've never imagined. The Oregon Cascade Mountains are a breathtaking stretch of rugged peaks and lush valleys. They run like a spine through the state's western half, part of the larger Cascade Range. This volcanic arc has been shaped by millions of years of intense geological activity. Here, Earth's tectonic forces clash, and molten rock rises to sculpt the land. This region isn't just a collection of towering mountains. It's a living, breathing landscape forged by fire and bound by time, whispering stories of its ancient origins. Over a dozen notable volcanoes exist in the Oregon Cascades. Each has its own personality, history, and potential for destruction. Among them is Mount Hood, the state's highest peak, standing tall at 11,240 feet. Known for its symmetrical cone and stunning glacier, Mount Hood is classified as a stratovolcano with a volcanic explosivity index, VEI, of 3. Though often tranquil and beloved by hikers and skiers, it last erupted in the 1790s and remains an active threat. Fumaroles and hot springs hint at its fiery heart. Further south, Mount Jefferson looms at 10,495 feet. Its jagged, glacial carved ridges give it a dramatic and untamed appearance. This stratovolcano, also with a VEI of 3, is considered dormant but not extinct. Its remote location makes it one of the least studied peaks, adding a layer of mystery to its imposing silhouette. The Three Sisters, a trio of volcanic peaks, dominate the Central Oregon Cascades. Each sister, north, middle, and south, has a distinct character. The North Sister is extinct, its crumbling basalt layers bearing witness to its ancient fiery past. The Middle Sister is dormant, while the South Sister, with a VEI of 3, is the most recently active. It shows signs of uplift in recent decades, a stark reminder that its story is far from over. Together, these peaks create a stunning and varied landscape. This landscape includes sharp ridges, alpine meadows, and glacial valleys. One of the most fascinating and violent volcanoes in the region is Crater Lake, or what remains of Mount Mazama. Around 7,700 years ago, this mighty stratovolcano unleashed a catastrophic eruption. Rated at a VEI of 7, it obliterated its summit and created the caldera that now holds one of the world's deepest and clearest lakes. Crater Lake, with its vivid blue waters and iconic Wizard Island, is a hauntingly beautiful reminder of the sheer power of volcanic activity. Other notable peaks include Newberry Volcano, a massive shield volcano with a VEI of 3. It is known for its extensive lava flows and unique obsidian deposits. Mount Bachelor, a young stratovolcano and popular ski destination, last erupted around 8,000 years ago. Broken Top, an extinct, heavily eroded stratovolcano, has jagged ridges that hint at its tumultuous volcanic origins. Each of these volcanoes is a chapter in the Cascades' volatile history. The VEI for these peaks typically ranges between 2 and 7, with most falling in the 3 to 4 range. This indicates eruptions capable of causing significant local devastation. Together, they form a landscape of staggering beauty and latent danger. It's a stark reminder of the dynamic forces shaping our planet. For those who visit, the Oregon Cascades are a place of awe and wonder, where every peak holds secrets of Earth's inner workings. Beneath the serene, snow-capped exteriors of the Cascade Range lies a reminder that Earth is alive and unpredictable, capable of inspiring creation and catastrophic destruction. This land, forged by fire, features mountains that breathe, where the next chapter in their story may yet be written. The Cascade Range of Oregon is more than picturesque volcanic peaks. Hidden beneath its rugged terrain is a vast subterranean aquifer, an enormous reservoir of water embedded within the volcanic landscape. Recent research by University of Oregon scientists, in collaboration with other experts, revealed the sheer magnitude of this water resource, estimated at 81 cubic kilometers. This aquifer holds nearly 3 times the water volume of Lake Mead and over half that of Lake Tahoe. This groundbreaking discovery redefines the region's water supply potential and provides critical insights into its connection with volcanic processes. The aquifer is embedded beneath the central Cascades, encased within volcanic rock formations at the mountain crest, acting like a colossal natural reservoir, much like a vast water tower perched atop the landscape. This revelation sheds light on a previously hidden facet of the Cascades and underscores the geological complexity of this volcanic arc. Scientists suggest this aquifer may be one of the largest of its kind, and similar reservoirs could exist elsewhere in the Cascade Range, potentially a region-spanning system of volcanic aquifers. This discovery emerged from a study focused on the Cascade Range's evolution and water movement within its geological structures. Researchers initially aimed to understand how the volcanic landscape had been shaped, but their findings unearthed a far-reaching water resource and its link to volcanic activity. Their work highlights the interplay between water and geological hazards, emphasizing how water movement through volcanic systems can influence these dynamic landscapes. The implications are significant, especially with growing climate change concerns. As droughts intensify and snowpack, a primary recharge source for the aquifer, diminishes, understanding this hidden water storage becomes vital. This vast underground reservoir could play a crucial role in regional water management, offering a potential buffer against water scarcity while deepening scientific understanding of volcanic and hydrological processes. The discovery reinforces the intricate relationship between geology, water, and climate change challenges, further elevating the importance of these mountains. Researchers estimated the aquifer's size by revisiting geothermal drilling data from the 1980s and 1990s. These projects, intended to explore geothermal energy, recorded temperature profiles at various depths. These records provided the key to understanding water movement through the volcanic rock layers. Typically, rock temperatures increase with depth, but groundwater flow disrupts this pattern by cooling deeper layers. By pinpointing the depth where temperatures rise again, researchers estimated groundwater penetration and mapped the aquifer, calculating its immense volume. This approach, unlike previous methods focusing on surface water, delved deep underground to uncover a far more extensive water reserve. While the 81 cubic kilometer estimate is staggering, it's considered conservative due to limitations in the original drilling data. These holes weren't designed for groundwater mapping, leaving data gaps. The actual water volume could be even greater, underscoring its significance. The discovery has implications far beyond water supply. This vast underground aquifer plays a crucial role in shaping volcanic activity. When magma interacts with groundwater, the resulting pressure can lead to explosive eruptions, altering landscapes and releasing ash and gases that disrupt air quality. Understanding the aquifer's scale and movement provides critical insights into regional volcanic hazards. The aquifer's future is uncertain. Its existence depends heavily on snowpack, its primary recharge source. As climate change accelerates, rising temperatures are shifting snow to rain, reducing the snowpack that feeds the aquifer. Without consistent snowpack, the aquifer's long-term viability is threatened. This underscores the vulnerability of this hidden resource and the need for further research to understand its dynamics and ensure its sustainable management in a changing climate. Sufficient snow accumulation means less water is absorbed into the volcanic rocks, threatening reservoir capacity and long-term viability. This hidden groundwater system is dynamic and currently robust, but its resilience is deeply tied to the availability of replenishing snow melt. Shifting climate patterns put the delicate balance that sustains this aquifer under increasing pressure, raising questions about its role in both water resources and volcanic activity in the decades to come. What happens if a water reservoir is found beneath an active volcano? The discovery of a significant water reservoir beneath an active volcano can dramatically alter the risk profile of that volcanic system. While water is often associated with life and renewal, beneath a volcano, it takes on a more dangerous role. The interplay between water and magma creates a volatile environment where the potential for explosive eruptions increases significantly. Understanding why this occurs requires a closer look at the powerful dynamics between water, heat, and pressure. When water stored underground comes into contact with magma, a cascade of rapid and violent processes begins. As the water is exposed to the extreme heat of the magma, it undergoes a sudden phase change, converting from liquid to steam. This transition is not just dramatic but explosive, as steam occupies significantly more volume than liquid water. The rapid expansion generates immense pressure within the volcanic system, often overwhelming the surrounding rock. This can result in phreatomagmatic eruptions, among the most explosive and destructive types of volcanic events. In such eruptions, magma is violently fragmented into ash and pumice, while shock waves ripple through the air and ground, amplifying the destruction. Volcanic explosivity is further enhanced by the presence of dissolved gases within the magma. Magma typically contains volatile compounds like water vapor, carbon dioxide, and sulfur dioxide, held under pressure. When additional water is introduced from a subsurface reservoir, it can amplify this effect by adding more gases. Under the extreme temperatures near the magma, water molecules can decompose into hydrogen and oxygen gases, further increasing the pressure. If the overlying rock cannot withstand this buildup, the result is often a catastrophic eruption. Comparing volcanic systems with and without significant subsurface water, the difference in eruptive behavior becomes clear. Dry volcanic systems tend to rely on the magma's composition and inherent gas content to determine explosivity. While these systems can still produce powerful eruptions, the presence of a water reservoir introduces an additional and unpredictable risk factor. The interaction of water and magma often amplifies the intensity of eruptions, making them far more destructive than they might have been in a drier system. A common question arises: could this water act as a natural coolant, tempering the magma's volatility? In theory, water has the potential to cool magma if it remains in contact for an extended period. However, in the real world, such interactions rarely happen under controlled conditions. Instead of gradually cooling the magma, the water typically flashes into steam almost instantly upon contact, driving explosive activity rather than cooling. Mitigating the conditions within a volcanic system is extremely difficult. The dynamic and extreme nature of these systems makes it nearly impossible for water to play a stabilizing role. History is filled with examples of water-driven volcanic explosions, highlighting the dangers of this interaction. The 1980 eruption of Mount St. Helens in Washington is a prime example. Groundwater played a significant role in fueling the explosive blast. Similarly, the catastrophic eruption of Krakatoa in 1883 was amplified by seawater infiltrating the magma chamber. This created one of the most powerful eruptions in recorded history. More recently, the 2022 eruption of Hunga Tonga Hunga Ha'apai in the South Pacific showed how seawater mixing with magma can trigger a massive explosion. This explosion sent shock waves around the world and altered the planet's atmosphere. The implications of finding a water reservoir beneath an active volcano are significant. It adds urgency to monitoring and hazard mitigation efforts. Regions surrounding these volcanoes face increased risks. These risks include explosive eruptions, ash fallout, pyroclastic flows, and long-term environmental consequences. This dynamic situation highlights the need for advanced research and monitoring technologies. Seismic imaging and thermal mapping are critical for identifying and characterizing hidden reservoirs. Robust early warning systems can provide communities with the time needed to prepare for possible eruptions. Understanding the relationship between water reservoirs and volcanic activity is essential for reducing the risk to human life and infrastructure. The discovery of water beneath a volcano is a vivid reminder of the interconnectedness of Earth's systems. It reveals the profound power locked within the planet, where fire and water can combine to create catastrophic force. These hidden reservoirs have the potential to shape landscapes and the course of human history. They remind us of nature's ability to both create and destroy. The discovery of this vast aquifer beneath the Cascade Range is a remarkable geological revelation. However, it brings forth significant concerns about its long-term sustainability. Climate change is reshaping precipitation patterns and reducing snowpack. This threatens the natural recharge process that sustains this water reservoir. A reduction in snowpack, coupled with increasingly erratic weather patterns, could diminish the volume of water replenishing this hidden resource. Scientists, including Gordon Grant and Leif Karlstrom, are now dedicated to unraveling the complexities of this aquifer to ensure its effective management. Grant has emphasized the importance of understanding the broader implications of this discovery. He noted that while the aquifer is a geological gift, it presents challenges that demand careful attention. He expressed concern about the potential consequences of severe winters with little or no snow and prolonged dry spells. He pointed out the pressing need to assess the impacts of such scenarios on this critical water source. This groundbreaking discovery highlights the indispensable role of scientific research in uncovering Earth's hidden resources. It also underscores the necessity of developing informed strategies to manage and protect these vital reserves in the face of climate change. As research continues on this big water tower hidden beneath the Cascades, scientists are working not only to preserve it as a dependable resource for future generations,